Hello and welcome to Lecture 9. This week we're going to go back to Chapter 9 in your textbook and we're going to be talking about sequences. Now, before I begin, let me say that Thomas's calculus is very good for differentiation and integration, but the section on sequences is not very good. So let me start by recommending a better book. If you also find that you're not happy with Thomas's calculus and you want to start looking for another book, this is the book that I recommend, Guide to Analysis by Mary Hart. What is a sequence? A sequence, or to be more precise, an infinite sequence, is an endless list of real numbers. The first number is A1, the second number is A2, A3, A4, and so on. The ... on the end here means that this list goes on forever. And there's no end to this list. And this list is in a particular order. Each one of these AJs represents a real number. These are the terms of the sequence. For example, if we looked at the sequence 2, 4, 6, 8, 10, 12, 14, 16, comma, ... comma, 2n, comma, ... The first term here, A1, is equal to 2. The second term, A2, is equal to 4. And the nth term, AN, is equal to 2n. The ... on the end means the sequence goes on, doesn't have an end. The ... in the middle between 16 and 2n means the same pattern of numbers between 16 and 2n. If we want to write the whole sequence, we can write this as open bracket, an, close bracket, from n equal to 1 to infinity. Or if we're being lazy, we can just write open bracket, an, close bracket. That means the whole sequence A1, A2, A3, A4, A5, A6, A7, etc. We might not want to start at 1. Let's say we want to remove the first 4 terms and we want to start with A5, A6, A7, A8, etc. We could write this as open bracket, an, close bracket, from n equals to 5 up to infinity. Let's do some examples. For example, let Bn be equal to 1 over n for all n in the natural numbers. Then Bn is the sequence 1, a half, a third, a quarter, a fifth, a sixth, etc. Or we might look at the sequence minus 1 to the power n multiplied by 1 over n between n is equal to 1 and infinity. This is the sequence minus 1 plus a half, minus 1 third plus a quarter, minus 1 fifth plus 1 sixth, etc. Next example, let xn be cos n pi. Then the sequence xn is minus 1, plus 1, minus 1, plus 1, minus 1, plus 1. Because cos pi, cos 3 pi, cos 5 pi, cos 7 pi, etc. are all equal to minus 1. Cos 2 pi, cos 4 pi, cos 6 pi, cos 8 pi, etc. are all equal to plus 1. Or, for example, the sequence 1 over n squared, but starting with n equal to 5, is the sequence 1 over 25, 1 over 36, 1 over 49, 1 over 64, etc. Perhaps the most famous sequence is the Fibonacci numbers, and we define them like this. A1 and A2 we say should be equal to 1. And then after that, each term of the sequence is the sum of the previous two. So for example, we're going to start with 1 and 1. To get the third term, we do 1 plus 1 is equal to 2. I'm drawing squares at the bottom. This is not a square of area 2. This is a square which has width 2 and height 2. So the area of this square is equal to 4. The makeup exams will cover exactly the same topics as the original exams. And then for the fourth term in the sequence, we do 1 plus 2 is equal to 3. Now, because of the way we're adding them up, you see we can put the squares touching in this picture. A square of side 3 touches a square of side 2 and a square of side 1. And then the next term, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Something you may have seen before in artwork is the Fibonacci spiral. If we draw a quarter of a circle inside each one of these squares, like this, and match them up, we get a spiral which is called the Fibonacci spiral. Okay, let's suppose that AN is a sequence. Now note that for every natural number small n, we have a real number an. So really we have a function which maps from the natural numbers to the real numbers. We can use this to formally define a sequence. What is a sequence really? A sequence of real numbers is a function a from the natural numbers to the real number. If we wanted to, instead of writing a subscript n, we could write a of n using our usual function notation. And the set of all sequences of real numbers, that's the same as the set of all functions from the natural numbers to the real numbers, we can write as r superscript n, r to the power n. Now, why do we use this notation? Well, one notation for a sequence is instead of writing a list, we could write brackets around our list. So we could write bracket 1, comma, a half, comma, a third, comma, a quarter, comma, a fifth, and so on. And then at the end, we could do another bracket. And that sort of looks like a vector. If we add the vector x, y, z, that would be a vector in R3. So we might expect the set of all sequences to be noted as r to the power infinity. But there's a problem with that notation. What does infinity mean? There's actually many different types of infinity, so we need to be more precise. What type of infinity do we want? We want the same type of infinity as the size of the natural numbers. So that's why it's r to the power n. More generally, b to the power a denotes the set of all functions from a set A to a set B, but we're not going to need that in this course. Now, even though sequences are really functions from the natural numbers to the real numbers, we don't want to think of them as functions in this course. We want to think of them as lists of numbers. For sequences, there's two things which are important: the order in which the numbers appear and the behavior of the terms as n tends to infinity. Let's go back to some examples of sequences. Let an be the sequence 1 over n. I've drawn a graph of this function. What does it look like? Look at the graph. What do we think happens when n goes to infinity? we think that an goes to 0. Another sequence, let bn be n plus minus 1 to the power n multiplied by 1 over n. So then we have the sequence 0, 2 and a half, 2 and 2/3, 4 and a quarter, 4 and 4/5, 6 and a sixth, etc. How does this sequence behave when n tends to infinity? It looks like bn goes to infinity as n tends to infinity. Another sequence. Sequence Cn is minus 1 to the power n plus 1 over n. This is a sequence 1, minus 1/2, plus 1/3, minus a quarter, plus a fifth, minus 1/6, etc. Look at the graph. What happens to Cn as n tends to infinity? Looks like Cn goes to 0 as n tends to infinity. A fourth example, let dn be the sequence 1 minus 1 over n. So that's the sequence 0, 1/2, 2/3, 3/4, 4/5, 5/6, etc. It looks from this graph that dn goes to 1 as n tends to infinity. And one more example. I'm going to need to define the floor function. The floor function is a function from the real numbers to the integers, and it's defined to be the biggest integer which is smaller than or equal to our number x. So in other words, it's rounding down. If we start with an integer such as 4 or minus 4, the floor function just gives us the same number. But if we start with a number which is not an integer, let's say we start with a number 3.79, it rounds down to the next integer. It rounds 3.79 down to 3. And if we're on a negative number, again, we're going down. So minus 3.79 is rounded down to minus 4. Using the floor function, we can define the sequence En, the floor function of n over 2 plus minus 1 to the power n over 2. And I can tell you that this is the sequence minus 1/2, 3 over 2. 1/2, 5 over 2. 3 over 2, 7 over 2. 5 over 2, 9 over 2, etc. Now, note that E2000, put 2000 into the formula in place of small n. It's 2000 divided by 2 is 1000. The floor function of 1000 is 1000, and then it's plus 1/2. Or we could look at E2 million. That would be 1 million plus 1/2. Certainly looks like En goes to infinity as n tends to infinity. But I've been saying looks like and goes to a lot here. But what does this mean mathematically? We need to be more precise. We need to start talking about limits of sequences. First of all, what does goes to infinity really mean? I'll tell you what it doesn't mean. It doesn't mean gets bigger, because the sequence dn gets bigger, but we think dn goes to 1. And moreover, the sequence en we think goes to infinity, but this sequence doesn't always get bigger. This goes bigger, smaller, bigger, smaller, bigger, smaller, bigger, smaller. So what does goes to infinity really mean? Here's a graph of the sequence En again. That's the one that I defined using the floor function. Know that if we draw a green line at height 2, then 4 points of the sequence are underneath the green line and all of the other points are above the green line. Well, if instead of height 2, I said, let's draw a line at height 4, then again, we have a finite number of points at the start of the sequence underneath the line, and all of the rest of the sequence is above the line. This would be true for any number. Let's zoom out a little bit. Again, this is the function en. Let's suppose we choose any number, capital A, and we draw a green line at height, capital A. Then there's going to be a finite number of points underneath the line and an infinite number of points above the line. One of the points underneath the green line is going to be the last one. I'm going to call this last one E capital N. And I've colored this in orange in the graph. If this is the last one underneath the line, then all of the points after this must be above the line. So En plus 1 must be above the line. En plus 2 is above the line. En plus 3 is above the line, and so on. In other words, there exists a capital N such that En is bigger than A for all n bigger than capital N. I want to introduce two symbols here, which I'm going to be using a lot. This upside down capital A means for all. If you try to remember which is which, there's an A in the word all. And this backwards capital E means there exists. It's an E because there's the letter E in exists. Now, obviously, the number n that we're finding is going to depend on capital A. So if we wanted to, we could write that n is a function of A, so that we always remember that n depends on A. For example, let's suppose we start with capital A as 10. Then note that if small n is bigger than 21, then En, and we can do the calculation, I'll leave this for you to check later, is bigger than or equal to 11 plus or minus a half. 11 plus or minus a half is bigger than 10, which is A. So that means that if we wanted to, we could choose capital N of 10 is equal to 21. If A is 10, we could choose capital N is 21. And then if we're after 21, all of the sequence is above the green line. Now, before we go on, let me remark that we don't always have to choose the best capital N. We could choose any capital N which works. 21 works, but then every number bigger than 21 also works. So, for example, if we wanted to, we could choose capital N is 1,000,000. And then the calculation still works. If small n is bigger than 1,000,000, then En is bigger than 10. Check it. Do the same calculation that I did on the previous page. Check that if small n is bigger than 1,000,000, then En is bigger than 10. Let's do a different A. Let's suppose now we have A is 100. Then I'm saying En is bigger than 100 for all n bigger than 201. And I leave this for you to check. That means we could choose capital N is 201. Let's do this in general. Let's suppose we have any positive number, capital A. And I'm saying we can always find a capital N for this sequence. And the way, in this example, the way that we could do this is we could say, let capital N be the smallest integer such that capital N is bigger than 2a plus 3. And if we choose that, if small n is bigger than capital N, then small n must be greater than or equal to 2a plus 4. But then n over 2 must be bigger than a plus 2. What's the smallest minus 1 to the power n over 2 could be. The smallest it could be is minus a half. And then the floor function of a plus 2. Remember, the floor function goes down a little bit. It doesn't go down a lot, just goes down a little bit. And then we do another minus a half, so we go down a little bit more, but we're still going to be bigger than a. If we choose n to be bigger than 2a plus 3, then small n bigger than capital N implies that En is greater than capital A. So now I'm ready to formally define the idea of diverges to infinity. A sequence of real numbers diverges to infinity if and only if, for all positive real numbers capital A, there exists a natural number capital N such that if small n is bigger than capital N, then An is bigger than capital A. If we have a sequence which diverges to infinity, we can write this in two ways. We could either write An tends to infinity as n tends to infinity, or we could write that the limit of An as n tends to infinity is equal to infinity. I'm aware that you studied limits in Mathematics 1, but I'm hoping that by doing more details here, by going deeper into the idea of limits, you can gain a deeper understanding of what a limit really means. I've written the definition of diverges to infinity, or limit is equal to infinity at the top. For all a greater than 0, there exists capital N in the natural number such that small n greater than capital N implies An is greater than capital A. We're going to be using this definition to prove some examples. For the first example, let's look at the sequence square root of n. And we're asked to show that An tends to infinity as n tends to infinity. I can show you the whole answer to this. Let a be greater than 0. Choose a natural number capital N such that n is greater than or equal to a squared. Then, for all n in the natural numbers, small n greater than capital N implies An is equal to the square root of small n. But small n is bigger than capital N, so that means square root of small n must be bigger than the square root of capital N. But because we said n must be bigger than a squared, square root of n must be bigger than a. So we're finished. That proves that An tends to infinity as n tends to infinity. Let's talk about the order of the answer. Let's talk about why the answer is written like this. Look at the yellow box at the top. The first part is for all a greater than 0. So the first part of our answer should be about capital A. The first part of our answer should let a be any positive number. The second part of the definition is there exists capital N. So the second part of our answer should be about capital N. It should be about proving that capital N exists. And the way we do that is we say which capital N we're going to choose. We're going to choose a natural number capital N such that n is greater than or equal to a squared. And then the third part of the definition is the implication. N is greater than capital N, then An is greater than A. So the next part of our answer should be about this. The next part of our answer should be proving that if small n is bigger than capital N, then An is greater than capital A. Let's do another example. And this time I'm going to show you how to find capital N. Let Bn be the natural logarithm of n. Show that Bn tends to infinity as n tends to infinity. Okay, so the answer should look like this. I'll explain the way that we write our answer. Let A be greater than 0. Second sentence is about capital N. Choose capital N such that, but let's leave it blank here. We don't know yet. Let's pretend that I don't know yet which capital N to choose. And then the answer continues. Then for all natural numbers small n, n greater than capital N implies Bn, or natural logarithm of n, is greater than. And again, let's leave it blank. I don't know what to write here yet, but I know that I want to finish with capital A. If we can fill in these two blanks, then we finish the answer. That would prove that Bn tends to infinity as n tends to infinity. So how do we fill in these blanks? What we need is a piece of scrap paper. What do we want to end up with? We want to end up with the natural logarithm of n is bigger than capital A. So I'm going to start by writing that on my scrap paper. I want to have the natural logarithm of n is greater than A, and I'm going to play around with this inequality. That's the same as saying we want to have n is bigger than e to the power A. But then from that, we know what capital N to choose. We can choose capital N to be bigger than e to the power A. Okay, good. Let's get rid of the scrap paper. We know how to fill these blanks in now. For the first blank, we can write, we're going to choose capital N to be bigger than e to the power A. And then we need to fill in the second blank. We need to prove that if small n is bigger than e to the power A, then the natural logarithm of n is bigger than capital A. So what we do is we take what we wrote on the scrap paper, basically, and we write it here. Natural logarithm of n is bigger than natural logarithm of capital N, which is bigger than natural logarithm of e to the power A, which is A. And then that's the full answer to this example. Let Cn be n squared, square root of n plus n squared plus 1 over n squared minus 43 if n is greater than or equal to 7, and let Cn be equal to 0 if n is between 1 and 6. Show that this sequence tends to infinity as n tends to infinity. Now, first let's look at our Cn. We're interested in what happens at the end of the sequence. We're not interested in what happens at the start of the sequence. So we can forget for now about the zeros between 1 and 6. Let's just think about what happens if we're after 7. Look at n squared square root of n plus n squared plus 1. How can we make this smaller? 1 is a positive number, so if we get rid of the 1, then we get smaller. N squared is a positive number, so if we get rid of the n squared, then we get smaller. So that gives us the first inequality. I want to simplify this further. Now let's look at the bottom. Let's look at n squared minus 43. I want to make the whole function smaller. And the way that I can make the whole function smaller is by making this bottom bigger, by making n squared minus 43 bigger. We move to minus 43 and we get bigger. N squared is bigger than n squared minus 43, so this whole function is smaller than the function before. And then, of course, the n squares cancel, and we're just left with square root of n. But then we have almost the same as a previous example. we start by saying let a be greater than 0, and then in the second sentence we need to choose n. In the previous example we were choosing a squared. Here we need to be just a little bit careful because this sequence is different at the start. So we want n to not only be bigger than a squared, we want n to also be bigger than 7. As long as we're bigger than 7, then we don't have to worry about the 0 at the start. And then for all n bigger than capital N, which we know is at least 7, Cn is bigger than square root of n, which is bigger than square root of capital N, which is bigger than a. So we've proved that Cn tends to infinity as n tends to infinity. Two remarks. Remember that we don't always have to choose the best or the smallest n. We only need to choose one which works. If you're given an exam question like this, you can still get full marks even if you don't have somehow the best or the smallest n. You only need to choose or prove the existence of a capital N which works. I've done 3 examples here. 2 of these ones it was easy to find a capital N. In the other one, I used an inequality first to make the formula a little bit easier so that I could find n. Time for a theorem. Let's suppose we have 2 sequences of real numbers, and let's suppose that an is always bigger than bn for some n greater than n0. If the smaller sequence tends to infinity, then the bigger one must also tend to infinity. Let's prove this. If we do a question about limits, tend to infinite limits, what's the first part of our proof going to be? It's always going to be let a greater than 0. So let's write that first. Since we know that Bn tends to infinity as n tends to infinity, we know that there exists some number n1 such that if n is greater than n1, then Bn is bigger than a. We know this because we know that Bn tends to infinity. Now we've got 2 capital N's. We have capital N1 and we have capital N0. What we're going to do is we're going to choose the biggest one of these. Let n be whichever one of these numbers is bigger, the maximum of n0 and n1. Then if we're bigger than capital N, we know 2 things. We know that an is always bigger than bn, and we know that bn is always bigger than capital A. But if we're bigger than capital N, that means that an must also be bigger than a. And that's the end of the proof. That proves that an tends to infinity as n tends to infinity. For example, let's suppose an is n squared plus n cos n pi, and bn is a half n squared. What's the first sentence of our calculation? The first sentence is always going to be let a be greater than 0. What's the second sentence going to be about? The second sentence is going to be about capital N. Now, I've already done my calculation on scrap paper here, so I already know that I want capital N to be bigger than the square root of 2a. And then that works for this calculation. If small n is bigger than capital N, this implies that bn is bigger than a. Therefore, bn tends to infinity as n tends to infinity. Now, as long as we're bigger than 2, forget about the first term of the sequence, as long as we're 2 or more, n squared plus n cos n pi is always the same as n squared plus n minus 1 to the power n, and that's always bigger than n squared minus n. If n is an odd number, then these two are going to be equal. If n is an even number, then we're going to have strictly greater than. Just make it smaller again. And this is the part where I'm using n is bigger than 2. I'm saying that we can replace the minus n by minus a half n squared. As long as we're bigger than 2, a half n squared is going to be bigger than n. But that's just exactly Bn. So what do we have? We have that Bn tends to infinity, and we have that An is bigger than Bn. Therefore, An also tends to infinity by the theorem. Let An be n squared plus the square root of n divided by n plus cos n. Show that this sequence tends to infinity as n tends to infinity. Well, I'll just leave the calculation here for you to check. First, we can show that there's be a typo here. Yes, this is wrong. First, we show that An is bigger than a half n, but a half n we know tends to infinity, so by the theorem, An must also tend to infinity. We can also talk about a sequence of real numbers which diverges to minus infinity. A tends to minus infinity as n tends to infinity. And this is the same as the previous definition, but just with two changes. Instead of insisting that we want An to be bigger than capital A, now I want to insist that An is less than minus A. It's true that An tends to minus infinity if and only if minus An tends to plus infinity. I leave that for you to check. Another theorem. Almost the same as the previous one. Let's suppose we've got two sequences, and let's suppose An is always less than Bn. Doesn't have to be true at the start of the sequence. We don't care what happens at the start of the sequence, but at the end of the sequence, we want this to be true. After some number n0, we want this to be true. If the bigger sequence, the Bn, tends to minus infinity, then the smaller sequence must also tend to minus infinity. And the proof is this. Bn tends to minus infinity, so minus Bn tends to infinity. Using the previous theorem, minus An must tend to plus infinity, so then An tends to minus infinity. I'll leave that for you to come back and read later. Look at the sequence minus 1 to the power n plus 1 divided by n. This is a sequence 1, minus a half, plus a third, minus a quarter, plus a fifth, minus a sixth, etc. And here's a graph of this sequence. What happens to this sequence when n tends to infinity? Well, it looks like the sequence goes to 0 as n tends to infinity, but how can we make this more precise? What we could do is we could draw two green lines, a green line at height epsilon and a green line at height minus epsilon. And then at the start of the sequence, there's a few points which are outside these lines, but apart from those, the rest of the sequence is going to be between the green lines. So for example, if we let epsilon be 1 over 100, then I'm claiming that yn is always between minus 100 and 100 for n greater than 100. You check that. In general, if we always chose n to be bigger than 1 over epsilon, then n greater than epsilon implies that yn is between minus epsilon and epsilon. In other words, if capital N is bigger than 1 over epsilon, n greater than capital N implies that the absolute value of yn is smaller than epsilon. We use this idea for the definition of a sequence which tends to 0. A sequence of real numbers tends to 0 if and only if, for all epsilon greater than 0, there exists a natural number capital N such that if n is greater than capital N, then the absolute value of n is smaller than epsilon. In mathematics, we have a convention. Usually we use the letter epsilon for arbitrarily small numbers, and we use a capital letter, for example, capital A, for arbitrarily large numbers. That's why I used capital A in the definition of a sequence which was tending to infinity, because I wanted it to be just some big number. If I have a sequence which tends to 0, I need to be thinking about just some small number. So I'm using epsilon for some small number. There's another name for a sequence which tends to 0. It's called a null sequence. Now, I've written the definition at the top in the yellow box. I want to use the definition to prove that the sequence n to the power minus 7 is a null sequence. What we need to do is we need to prove that an tends to 0 as n tends to infinity. So our answer is going to look like this. The first sentence is going to be about epsilon. The second sentence is going to be about capital N. And then in the third sentence, we're going to do the calculation. So let epsilon be greater than 0, full stop. Choose something, full stop. Then for all n in the natural numbers, n greater than capital N implies that the absolute value of an, and I want to say, is smaller than epsilon. So I need my scrap paper again. Let's start with what we want. I want to have that the absolute value of 1 over n to the power 7 is less than epsilon. N is a positive number. N is a natural number. All the natural numbers are positive. So that's just the same as saying 1 over n to the power 7 is smaller than epsilon, or n to the power 7 is bigger than 1 over epsilon, or n is bigger than 1 over epsilon to the power 1 over 7. Then I know which capital N to choose. As long as we choose capital N to be bigger than epsilon to the power minus 1 over 7, then this calculation is going to work. Okay, get rid of the scrap paper. We can start filling in the answer. First, we're going to choose capital N is greater than or equal to epsilon to the power minus 1 over 7. And then we can fill in the calculation. Absolute value of an is the same as 1 over n to the power 7. That's smaller than 1 over capital N to the power 7, which is smaller than epsilon. Look at the sequence. Zn is 1 minus 1 over n. This is the sequence 0, a half, 2/3, 3/4, 4/5, 5/6, etc. It looks like the sequence goes to 1 as n tends to infinity, but this is mathematics, and in mathematics we need to be precise. A sequence of real numbers, an, tends to L as n tends to infinity, if and only if all epsilon greater than 0, there exists capital N in the natural number such that if small n is greater than capital N, then the absolute value of an minus L is smaller than epsilon. We could also write that the limit as n tends to infinity of an is equal to L, if this is true. What about this sequence? Let un to be equal to 7 if n is greater or equal to 7, or equal to n if n is between 1 and 6. So we have the sequence which goes 1, 2, 3, 4, 5, 6, 7, 7, 7, 7, 7, 7, 7, 7. Let's write the answer. How does the answer start? The answer is always going to start, let epsilon be greater than 0. What is the second sentence going to be? The second sequence is going to be about capital N. And because I've already done my calculation, I know that I can choose capital N as 6. Then if small n is bigger than capital N, this implies n is bigger than 7, which implies un is equal to 7, which implies the absolute value of un minus 7 is equal to 0. And 0 is smaller than epsilon. That proves that un tends to 7 as n tends to infinity. Here's another example. Show that this sequence tends to a half. Well, later I'm going to need Vn minus a half. So I'm going to start by simplifying this. And you can check that that's the same as 2n plus 1 over 2, 2n squared plus 1. So the absolute value of this, and again I'll leave this for you to check, is smaller than 3 over 4n. I do a quick calculation on scrap paper and I realize I want to choose capital N to be bigger than 3 over 4 epsilon, and then the calculation works. Small n is bigger than capital N, then the absolute value of Vn minus a half is smaller than 3 over 4n, which is smaller than 3 over 4 capital N, which is smaller than epsilon. Therefore, Vn tends to a half as n tends to infinity. I know I've gone quickly here. You can come back and check this later. Another idea. Let's define a sequence Pn like this. First 3, then 3.1, then 3.14, 3.141, and so on. I want Pn to be the first n digits of pi. Show that Pn converges to pi as n tends to infinity. Okay, so note what we have. What's the difference between P1 and pi? The difference is going to be 0.14592, etc., etc. That's smaller than 1. What's the difference between P2 and pi? 0.041592, etc. The difference between these two numbers is going to be smaller than 0.1. The difference between P3 and pi is going to be smaller than 0.01, and so on. The difference between Pn and pi is always going to be smaller than 10 to the power 1 minus n. So let epsilon be greater than 0. Choose capital N to be bigger than 1 minus log base 10 of epsilon. Then, here's the calculation. If small n is bigger than capital N, Pn minus pi is smaller than, so the absolute value of Pn minus pi is going to be smaller than 10 to the power 1 minus n, which is smaller than 10 to the power 1 minus capital N, which is smaller than 10 to the power 1 minus log base 10 of epsilon, but that's just equal to epsilon. How did I know which capital N to choose? I used my scrap paper. I started with what I wanted. I started with 10 to the power 1 minus n is smaller than epsilon. I rearranged that and I found the capital N that I wanted. That proves that Pn tends to pi as n tends to infinity. Next, I want to state that a sequence of real numbers cannot have more than one limit. Let's prove that. Let's suppose we have a sequence and let's do different cases. First, let's suppose that this sequence tends to a real number L, and it also converges to a real number M. We want to prove it has only one limit. In other words, we want to prove that L is equal to M. And the way to do this is we're going to start by assuming the opposite and then finding a contradiction. This is called proof by contradiction. So we start by assuming the opposite of what we want to prove. I want to prove that L is equal to M. So I'm going to start by assuming that that's not true. Start by assuming that L is not equal to M. Then L minus M is not 0, and the absolute value of L minus M is strictly positive. Divide this by 2 and call this epsilon. Now, because an tends to L, there must exist some number n0 such that if n is bigger than n0, then an is close to L. But an also tends to M, so there's going to exist another number. There should be a 1 here. Such that if we're bigger than n1, then an is close to M. Let capital N be the biggest of these two numbers, and then look at what happens after capital N. If we're bigger than capital N, then L minus M, we can show is smaller than L minus M. But a number can't be strictly less than itself. This is an inequality. This is a contradiction. Because L not equal to M leads to something which is not true, we must have that L is equal to M. This means that a sequence cannot have two different finite limits. Case 2. Again, let's suppose we start by assuming that an tends to a real number L. But then, using epsilon equal to 1, an must always be between L minus 1 and L plus 1. So an does not tend to infinity and an does not tend to minus infinity. That proves that a sequence cannot have both a finite limit and an infinite limit. There's one more case we need to look at. Is it possible to have a sequence which tends to both infinity and minus infinity? The answer is no, but I'm going to leave that for you to prove. That's the proof that a sequence cannot have two different limits. Let Zn be the sequence 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, etc. Show that Zn does not converge to 0 as n tends to infinity. Let me go through this quickly. If we try to show the opposite of a definition, then instead of doing it for all epsilon, we just need to find one epsilon where it goes wrong. So I'm going to choose an epsilon, and I'm going to choose epsilon as a half. Again, next part changes. Instead of showing there exists an n, instead of choosing an n, we need to do it for all n. So let n be any natural number. If n is odd, we're going to choose small n to be n plus 2. If capital N is even, we're going to choose small n is n plus 1. Then clearly small n is bigger than capital N, but the absolute value of Zn is bigger than epsilon. That proves that Zn does not converge to 0 as n tends to infinity. A sequence is called a convergent sequence if it has a real limit. The previous theorem says that a convergent sequence can have only one limit. A sequence which is not convergent is called a divergent sequence. That's the sequences which don't have a limit, but also the sequences which converge to infinity and the sequences which converge to minus infinity. I'll just remind you that if the limit is infinity, we say that the sequence diverges to infinity. If the limit is minus infinity, we say that the sequence diverges to minus infinity. For example, minus 1 to the power n, minus 1 to the power n multiplied by n, and n squared. These are all divergent sequences. The first two do not have a finite limit or an infinite limit. The third one diverges to infinity. One more topic before we take a break. I want to talk about bounded sequences. A sequence is called a bounded sequence if the sequence is always between m and minus m. Precisely if there exists some number capital M such that the absolute value of A is always less than capital M. Theorem. Every convergent sequence is bounded. We'll start with a convergent sequence. We'll call it AN. That means there exists some number A such that AN converges to A as n tends to infinity. So in other words, if we use epsilon is equal to 1, there exists some number capital N such that small n is bigger than capital N, then the absolute value of AN is less than the absolute value of A plus 1. Okay, so think about the graph like this. We know that after n, we're going to be between absolute value of A plus 1 and minus the absolute value of A minus 1. So we know we're going to be between these lines, but we don't know what happens between 1 and capital N. So we need to take care of that. We're going to let capital N be the maximum of these numbers. The first capital N values of the absolute value of the sequence, and then this extra number, capital A plus 1. Then we know we're always going to be between capital M and minus M. That proves that AN is a bounded sequence. And now we should take a break. Today's going to be a long lesson. Let's take a break until 2:15. And now let's continue. We still have lots of ideas of sequences that we need to cover. Next, I want to talk about 5 rules for sequences: the sum rule, the constant multiple rule, the product rule, the quotient rule, and the sandwich rule. First, the sum rule. Suppose that AN converges to A and BN converges to B. Then AN plus BN converges to A plus B. Let's go through the proof of this very quickly. First sentence, of course it is, let epsilon be greater than 0. Because AN converges to A and BN converges to B, we know that there must exist some number capital N such that AN is going to be between A minus epsilon over 2 and A plus epsilon 2, and BN is also between B minus epsilon over 2 and B plus epsilon over 2. I've actually skipped a step here. We should really do this for an N1 and N2 first, and then let N be the maximum of these two numbers. If we add these together, we see that AN plus BN must be between A plus B minus epsilon and A plus B plus epsilon. And then that's the end of the proof. Therefore, AN plus BN converges to A plus B. The constant multiple rules, suppose that K is a number and AN is a sequence, which converges to A, then KAN must converge to KA. I'm not going to prove this, I'll leave this for you to do. Using the same ideas as the previous proof, you should be able to write a proof of this. The product rule, suppose that AN converges to A and BN converges to B, then A and BN converges to AB. Let's prove this, and this is a longer proof. First of all, BN converges to B, so BN is convergent, so BN is bounded. By a theorem which we did earlier today, just before the break. So that tells us that there exists some number capital M such that the absolute value of Bn is less than capital M. Now note that epsilon divided by capital M plus the absolute value of A, these three numbers are all positive. Positive divided by positive plus positive. This is positive. Because AN converges to A and BN converges to B, there must exist some number capital N such that small n is bigger than capital N. The distance between AN and A is always smaller than this number, this positive number, epsilon over M plus capital A. And the distance, or the difference between BN and B, is also smaller than this. But then we can finish the proof. If we're bigger than capital N, I want to show that this is smaller than epsilon. And the way I do it, first I'm going to subtract and add the same thing. Subtract ABN and then add ABN. And then I'm going to use the triangle inequality to split that into two absolute values. I have absolute value of AN minus A multiplied by absolute value of BN plus absolute value of A multiplied by absolute value of BN minus BN. Now, what do we have? The first one is smaller than epsilon over M plus absolute value of A. BN is bounded, so it's smaller than M. Absolute value of A, keep that as it is. And then the final one is also smaller than epsilon over M plus absolute value of A. Simplify this and we just have epsilon, and that's the end of the proof. The quotient rule. Suppose that AN converges to A, BN converges to B, and one more thing, suppose that B is not 0. Then AN divided by BN converges to A over B. I'm going to admit the proof for this theorem. We don't have time to prove this as well. So let's move on to example. Let AN be n to the power 5 plus 7n cubed plus 5n squared plus 8 divided by 5n squared plus 3n to the power 4 plus 27. Find the limit. The biggest term is n to the power 5. I want to divide the top and the bottom by n to the power 5. N to the power 5 divided by n to the power 5 gives 1. 7n cubed divided by n to the power 5 is 7n to the power minus 2, and so on. Then we can take the limit of each one of these component terms. 1 plus 0 plus 0 plus 0 divided by 5 plus 0 plus 0, or 1/5. The final rule is the sandwich rule. Let's suppose we've got 3 sequences which satisfy that AN is smaller than BN is smaller than CN for all n bigger than n0. Now, looking at the picture at the bottom, we don't care what happens at the start of the sequence. We don't care what happens in this red band. We only care what happens at the end of the sequence. And at the end of the sequence, we must always have the orange is smaller than blue is smaller than purple. Back to the theorem. If AN converges to L and CN converges to L, then the middle sequence must also converge to L. Let's prove this. How do we start? The same way we always start, let epsilon be greater than 0. What do we know? We know that AN converges to L, so we know that this must be true. And we know that CN converges to L, so this must be true. What do we do whenever we have two capital N's, capital N1 and capital N2? We pick the bigger one. And also, we'll pick the bigger out of N0, N1, and N2, so we don't have to worry about the inequality not being true at the start of the sequence. But then, if we're bigger than N0 and bigger than N1 and bigger than N2, then this is true. If we're bigger than N0, then Bn must be between AN and CN. If we're bigger than N1, then AN must be bigger than L minus epsilon. And if we're bigger than N2, then CN must be smaller than L plus epsilon. So that proves that Bn is between L minus epsilon and L plus epsilon. That proves that Bn converges to L as n tends to infinity. Let Cn be a sequence of real numbers such that Cn is always positive after n0. Suppose that Cn converges to C, then C must be greater than or equal to 0. I'm not going to prove this. Let's admit this proof. We don't have time to prove everything today. A corollary of this is we have two sequences such that AN is always smaller than BN, always after N0. We don't care what happens at the start of the sequences, but just what happens at the end of the sequence. So suppose that AN is smaller than BN after some number N0. Suppose that AN converges to A and BN converges to B, then A is smaller than B. A question for you to think about. I've just said that if AN is less than or equal to BN, this implies that the limit of AN is less than or equal to the limit of BN. Is this also true if we replace the less than or equal signs with strictly less than? And the answer is no. Why is it no? Let me show you an example. Think about the sequences 1 over n and 1 over n squared. Then if n is equal to 1, the two sequences are equal, but if n is bigger than 1, an is always smaller than bn. I think that's a mistake. It should be the other way around. An is always greater than bn. But the limits of these two sequences are both 0. An is strictly greater than bn, but the limits are the same. So let me just warn you, be careful when you take limits of inequalities. The correct rule to use is that an strictly less than bn implies that the limit of an is less than or equal to the limit of bn. Now, let an be a sequence. If an tends to infinity as n tends to infinity, then 1 over an tends to 0 as n tends to infinity. I'm going to skip the proof. You can come back and pause the video here or read the slides and check this proof. Let's think about cos n divided by n. This is always between minus 1 over n and 1 over n. 1 over n tends to 0, minus 1 over n tends to 0. So by the sandwich theorem, cos n divided by n tends to 0, as n tends to 0. N to the power 5 plus n to the power 4 cos n plus 6 divided by 4n to the power 5 plus n to the power 3 plus cos n. The biggest term here, again, is n to the power 5, so let's divide everything by n to the power 5. 1 plus cos n over n plus 6n to the power minus 5 over 4 plus 1 over n plus cos n over n to the power 5. Take the limit of each of these terms, we get 1 plus 0 plus 0 divided by 4 plus 0 plus 0, or 4, or 1 over 4. Okay, before we go further, we need to talk about some standard sequences. Let's talk about n to the power alpha, a to the power n, a to the power 1 over n to the power 1 over n factorial, and n over n. And ask, I'm interested in what are the limits of these 6 sequences. First one, if alpha is a real number, then n to the power alpha tends to either infinity, 1, or 0, depending on if alpha is positive, 0, or negative. Let's prove this. First of all, case 1. What happens if alpha is strictly positive? Then if we choose capital N such that alpha natural logarithm of capital M is bigger than natural logarithm of A, then we can show that n to the power alpha is bigger than capital A. That proves the first case. Case 2, that's an easy one. Clearly, if we have n to the power 0, then we always have 1. So we just have the sequence 1, 1, 1, 1, 1, 1. And that sequence must converge to 1. And then finally, if we're on case B, we're going to use case 1. Let beta be minus alpha. Then n to the power beta must tend to infinity, and therefore n to the power alpha, which is 1 divided by n to the power beta, must tend to 0. Next sequence, a to the power n. This tends to either infinity or 1 or 0, depending on if a is strictly greater than 1, equal to 1, or if the absolute value of a is less than 1. If a is less than or equal to minus 1, then the sequence does not have a limit. The sequence diverges. Very quickly, let's go through the proof. First, let's suppose that A is strictly positive. Let's introduce a new number h to be a minus 1. So if a is greater than 1, then h is greater than 0. Using this calculation, I'll leave this for you to check, I can show that an is bigger than 1 plus nh, which tends to infinity. So therefore, a to the power n must tend to infinity. Case 2. If a is equal to 1, then we just have the sequence 1, 1, 1, 1, 1, 1. So the limit must be 1. Case 3, if we're between 0 and 1, what we could do is we could let b be 1 over a trick we used before. B to the power n must then tend to infinity, so therefore a to the power n, 1 divided by b to the power n must tend to 0. If a is equal to 0, another easy one, we just have the sequence 0, 0, 0, 0, 0, 0, which has limit 0. Case 5, what if we're between minus 1 and 0? Then this is a triangle inequality. No, sorry, this is a sandwich rule proof. An must be between the absolute value of an and minus the absolute value of an, but that tends to 0 and tends to 0. So by the sandwich rule, this must tend to 0. Finally, what happens if an is less than or equal to minus 1? Then the sequence jumps between something which is positive, something which is negative, something which is bigger than 1, something which is less than minus 1, bigger than 1, less than minus 1, bigger than 1, smaller than minus 1. So it can't tend to a finite limit and it can't tend to an infinite limit. Now a question for you, have a guess. Suppose that a is greater than 1 and alpha is greater than 0. We know that an tends to infinity and we know that n to the power alpha tends to infinity. But which one of these is dominant? Which one is more powerful? What happens to an divided by n to the power alpha as n tends to infinity? Well, for example, let's suppose a is 1.001 and alpha is 101. Then the sequences look like this. They're both increasing. An is increasing quite slowly. 1.001 to the power 1000 is approximately 2.7, but 1000 to the power 101 is 10 to the power 303. So what happens to 1.001 to the power n divided by n to the power 101. It might surprise you to learn that the limit of this is actually infinity. So well done to the 6 people that correctly guessed infinity. Let's prove this. Let's suppose that a is greater than 1 and alpha is greater than 0. Then a to the power n divided by n to the power alpha converges to infinity as n tends to infinity. Now, the calculation is actually quite complicated to prove this for any number, so I'm going to simplify this a little bit. First, instead of looking at alpha, let's look at a natural number, p. I want to prove that an over n to the power p converges to infinity as n tends to infinity, and then if that's true, the bigger one, a to the power n over n to the power alpha, would also tend to infinity. Now, we could prove this for any natural number p, but the proof gets really complicated and the notation is complicated. So I'm actually only going to show you the proof if p is equal to 2. And then I'm just going to note about how we would change the proof for different values of p. First, since a is greater than 1, h equal to a minus 1 must be positive. Calculation looks like this. If n is bigger than 4, an over n squared. Remember I said I'm just going to do this for p equal to 2. So I'm just doing it with n squared on the bottom. That's 1 plus h to the power n over n squared. Multiply out 1 plus h to the power n, we get this thing. And I'm only interested in one of these terms. I'm only interested in the third term. So forget about everything else. That's bigger than n minus 1, n minus 2 over 3 factorial, h cubed over n squared. Why did I want this one? Because I want the powers of n on the top to be 1 bigger than the powers of n on the bottom. Because I have n squared on the bottom, I want 1, 2, 3 n's on the top. This simplifies to nh cubed over 24, and of course that tends to infinity as n tends to infinity. How would we change this if we had a different number? Let's suppose instead we had n cubed here. Instead of n bigger than 4, we would need to have a 5. Instead of choosing this one, we would actually have to choose the next one, because I would need to have 4 n's on the top to balance out with the n cubed on the bottom, and so on. I could write down the proof for any p, but it gets complicated and more complicated as p gets bigger. We just keep increasing these two things. We increase the number here, and with the term we take the 4th one, the 5th one, the 6th term, the 6th, 7th one, etc. As long as we're choosing the correct term, everything will cancel and we'll end up with n multiplied by something which tends to infinity. So, as I just said, a similar argument shows that an over np tends to infinity as n tends to infinity for all natural numbers p. And then a theorem from earlier today proves that an over n alpha also tends to infinity as n tends to infinity. A corollary. Now, we were talking about an divided by n to the power alpha, and we said that tends to infinity. Turn the fraction upside down, and we get something which converges to 0. Or if instead of number a which is greater than 1, we had a number b between -1 and 1. We could also show that n to the power alpha, b to the power n converges to 0 as n tends to infinity, just by changing the formula at the top. Another lemma. What happens to a to the power 1 over n? If a is a positive number, then a to the power 1 over n converges to 1 as n tends to infinity. And I'm actually going to skip the proof of this. I don't think we've got time to talk about this. It's another sandwich rule proof. You can check this later. N to the power 1 over n converges to 1 as n tends to infinity. It's a sandwich rule proof again. Let Kn be the difference between n to the power 1 over n and -1. Then we write n is 1 plus Kn to the power n. Multiply that out and then just pick one of these terms. Which one do we want? We want this one. So forget about everything else. And then rearrange it to prove that Kn is always between 0 and the square root of 2 over n minus 1. By the sandwich rule, Kn must converge to 0, and therefore n to the power 1 over n must converge to 1. Again, you can come back and read that in more detail later. What about a to the power n divided by n factorial? A to the power n tends to infinity. N factorial also tends to infinity. But what about their quotient? It tends to 0. Because n factorial is more powerful than a to the power n. I'm going to skip this proof. What about n factorial and n to the power n? Which is more powerful? Which is dominant? N to the power n is more powerful than n factorial. This quotient tends to 0. I can prove this just by writing down what do we have. N factorial is n minus 1, n minus 2, multiplied by n minus 3, etc. And n to the power n is just n. We have something which is smaller than 1 divided by n, but that tends to 0. So by the sandwich rule, this sequence tends to 0. So let's do a summary of these standard limits. First of all, n to the power alpha tends to either infinity or 1 or 0, depending on alpha. A to the power n also tends to infinity or 1 or 0. It does not have a limit, depending on the value of a. A to the power 1 over n converges to 1, and n to the power 1 over n converges to 1. A to the power n is more powerful than n to the power alpha, so this tends to infinity. But n factorial is more powerful than a to the power n. This quotient tends to 0, and n to the power n is more powerful than n factorial. This quotient tends to 0. Now that we have these standard limits, we can find the limits of things like this. N to the power 7, 7 to the power n, plus n to the power 5, 5 to the power n, divided by 3 to the power n, plus 8 to the power n. Which of these 6 things is the most powerful one? The answer is 8 to the power n. A to the power n is more powerful or dominant than n to the power alpha, and the biggest number here is 8. So what we do is we divide everything by 8 to the power n. And then we can look at each term separately. First of all, we've done this, n to the power a number multiplied by a number which is between -1 and 1 to the power n. What happens to this? The limit is equal to 0. And then again, n to the power 5 multiplied by a to the power n, but a is between -1 and 1, also tends to 0. 3/8 to the power n tends to 0. So we get 0 plus 0 divided by 0 plus 1, or 0. Another one, n factorial plus 8 to the power n divided by 7 factorial plus n to the power plus n factorial. So question for you, which of these terms is dominant? N factorial, 8 to the power n, or 7 to the power n? Okay, 2 people saying n factorial, 2 people saying a to the power n. The answer is n factorial. So we divide every term by n factorial. 1 plus something which will have limit 0 divided by something which will have limit 0 plus 1. Take the limit, we get 1. Let r be greater than 0, and think about the sequence 4 to the power 10 plus r to the power n, all to the power 1 over n. Calculate the limit of this sequence. Well, there's 2 cases to think about. If r is between 0 and 1, and if r is greater than 1. First of all, if r is between 0 and 1, we can use the sandwich rule. First of all, an, that's this thing, is always bigger than 4 to the power n to the power 1 over n, if we just remove the rn. How could we make this thing bigger? We could replace rn by something that's bigger than it. R is less than 1, then r to the power n is less than 1. So replacing the plus r to the power n by plus 1, we get to something which is bigger. But then we're sandwiched between 1 and 1. So the limit must be equal to 1. Case 2, what happens if r is greater than 1? Well, we're not interested in what happens at the start of the sequence, we're only interested in the end of the sequence. So it's going to be okay to think that we always have r to the power n is bigger than 4 to the power 10. Certainly that will be true for n bigger than some natural number n. And then we go back to the sandwich rule again. First of all, look at this bit I've underlined in green. 4 to the power 10 is smaller than r to the power n, so that's true. And on the left, let me choose take a different color. Now I'm underlining in orange. Just remove the 4 to the power 10 and it gets smaller. Take the limits of each side, we get r on the left and r on the right. We're sandwiched between r and r, so by the sandwich rule, the limit must be equal to r. The next idea is monotonic sequences. A sequence is called an increasing sequence if and only if an is always less than or equal to an plus 1. Now, just give you a warning, your Thomas's calculus book uses a different term here. So it's called an increasing sequence. It uses this unusual non-decreasing sequence. Just be aware that what I'm calling increasing sequence, your book is using this non-standard non-decreasing sequence term. And a sequence is called a strictly increasing sequence if we have the same thing, but instead of less than or equal to, we have strictly less than. And of course, we have the same definitions for decreasing sequence and strictly decreasing sequence. A sequence is called a monotonic sequence if it's either an increasing sequence or it's a decreasing sequence. So it's either always going up or level, or it's always going down or level. Let's talk about bounded sequences again. A sequence is bounded above if the sequence is always less than capital M. This number, capital M, is called an upper bound for the sequence. And we also have the idea of bounded below and lower bound. The sequence is bounded below if there exists some number, typo here, should be small m, some number small m such that the sequence is always bigger than small m. Small m is called the lower bound. Some examples. This sequence, Bn is equal to n. This is increasing. It's also strictly increasing. The sequence is always going upwards. That means it's monotonic. Because the sequence is always bigger than 0, it's bounded below. But it's not bounded above because it keeps getting bigger and bigger and bigger. We can't find a number m which is bigger than every term in the sequence. This sequence is increasing and strictly increasing. It's monotonic, it's bounded above, and it's bounded below. And this sequence, the sequence 1, is increasing because the definition of increasing had less than or equal to, but it's not strictly increasing. This sequence is decreasing, but not strictly decreasing. It's monotonic, bounded below, and bounded above. For an upper bound and lower bound, you can choose any number that works you want. So for this sequence, it's true that, typo just here, it's true that dn is always less than or equal to 567. Let AN be an increasing sequence. If AN is bounded above, then AN converges. If AN is not bounded above, then AN tends to infinity, as n tends to infinity. This is an important theorem. We're going to need some theory before we can prove this theorem. This is a theorem we're going to be using next week and the weeks after. So let S be a set. We say that the set is bounded above, same idea as sequence. If X is less than or equal to capital M for some capital M. Capital M is called the upper bound, and we have the same idea for bounded below. So just as we did for sequences, we're doing the same thing for sets. So for example, if S is the set containing numbers 1, 2, 3, and 4, then for every X in the set, X is smaller than 7. So 7 is an upper bound for S. Now note that 5 is also an upper bound for S. If X is in S, we could write that X is less than or equal to 5. 4 is also an upper bound for S. These four numbers, 1, 2, 3, and 4, are all less than or equal to 4. So 4 is an upper bound. But 3.99999 is not an upper bound for the set S because, of course, 4 is bigger than 3.9999. So 4 is, in fact, the least upper bound for S. Let's make this more precise. This is called the supremum of S, and we write this as SUPS. This is the least upper bound for the set S. If S is the empty set, we write that the supremum of S is minus infinity. If S is not bounded above, then we define the supremum of S to be infinity. So, for example, the supremum of the set 1, 2, and 3 is 3. The supremum of the closed interval from 0 to 1 is 1. The supremum of the open interval between 0 and 1 is 1. The supremum of the integers is infinity, and the supremum of the empty set is minus infinity. This is almost the same as maximum, but not quite. The maximum of 1, 2, and 3 is 3. If the maximum exists, then it's the same as the supremum. The maximum of the closed interval between 0 and 1 is also 1. But the maximum of the open interval between 0 and 1, or the maximum of Z, or the maximum of the empty set, do not exist. So you could think of this idea of supremum as a more clever or a more sophisticated idea than a maximum. As long as the maximum exists, it's the same as the supremum, but if the maximum doesn't exist, we might still have a supremum. We also have a smarter or more clever minimum, and this is called the infimum. This is the greatest lower bound. And again, if S is empty, we define the supremum. This is a typo. That's infimum of S should be infinity. And if S is not bounded below, we define the infimum of S to be minus infinity. Lots of typos today, I'm afraid. I'm going to fix those later. So, for example, the infimum of the set minus 1, 0, 7, 11 is minus 1. The infimum of the half open interval from 0 to 1 is 0. The infimum of Z is minus infinity. The infimum of N is equal to 1. Is that the same as the minimums? The minimum of the first set is minus 1. The minimum of the half open interval between 0 and 1 does not exist. I'm sorry, where was I? Minimum of the first set is -1. The minimum of the half open interval and z do not exist. The minimum of the natural numbers is equal to 1 because the smallest natural number is equal to 1. A lemma. Let's suppose that S is a subset of the real numbers and S is not the empty set. Then the supremum of S is equal to alpha if and only if two things are satisfied. X is always less than or equal to alpha for all x in S, and for all epsilon greater than 0 there exists xn in S such that x0 is between alpha and alpha minus epsilon. So what that means is if S looks like this, and if the supremum is here, then it doesn't matter how small epsilon is, we can always find something in the set which is close to alpha, within epsilon of alpha. And the proof looks like this. First of all, let's prove is implied by. Rule number 1 implies that alpha is an upper bound for S, and rule number 2 implies that alpha minus epsilon is not an upper bound for S. That proves that alpha is the least upper bound or the supremum. And going forwards, implied is straightforward. If alpha is the supremum, alpha is the least upper bound, so therefore 1 and 2 are true. We need the completeness axiom. An important part of mathematics that calculus is based on. Every non-empty set of real numbers, which is bounded above, has a supremum. Okay, now that we have enough to prove the important theorem, let me repeat. If AN is an increasing sequence, which is bounded above, then AN converges. If we have an increasing sequence which is not bounded above, then AN tends to infinity, as N tends to infinity. First, let S be the set containing all of the numbers in the sequence. If the sequence is bounded above, then this set is also bounded above. And then by the completeness axiom, S must have a supremum. Let's give this supremum a name. We'll call this supremum alpha. Because we're talking about convergence, we also need an epsilon. Now, epsilon be greater than 0. Then alpha minus epsilon is not an upper bound for S. Alpha is the least upper bound. So any number smaller is not an upper bound. So there must exist a term in the sequence which is between alpha minus epsilon and alpha. If that wasn't true, then alpha minus epsilon would also be an upper bound, but we know it isn't an upper bound. Because AN is an increasing sequence, if n is bigger than n, AN is bigger than A capital N. So A small n must also be between alpha and alpha minus epsilon. That's enough to prove that AN converges to alpha. An increasing sequence, which is bounded above, converges to its supremum. Part 2. Now I want to show that if the sequence is not bounded above, then it converges to infinity, or diverges to infinity, I should say. So for diverges to infinity, we start with an arbitrary big number. Start by writing let capital A be greater than 0. If AN is not bounded above, then A is not an upper bound for AN. So there must exist a term in the sequence which is bigger than capital A. But we have an increasing sequence. If A capital N is bigger than A, then everything after that in the sequence must also be bigger than capital A. And that's enough to prove that AN must diverge to infinity as N tends to infinity. Two corollaries of this theorem. If AN is an increasing sequence, then these two things are equivalent. A is convergent if and only if AN is bounded above. And we could do the same thing for decreasing sequences. If AN is a decreasing sequence, then the sequence is convergent if and only if it's bounded below. Combine these together, we get a very famous theorem called the Monotonic Sequence theorem. Every bounded monotonic sequence converges. And finally, that is the end of this week's lecture. This week I almost used the whole 2.5 hours. Let me ask you, do you have any questions?